In this video, we will be talking on the other half of chapter 3, that is heat transfer from extended surfaces. This is a very important concept, and it has a wide variety of real life applications. You might have heard about fins being attached to a radiator or heat exchanger, and various other applications which we will be talking during this video. So let's answer the basic question: why do we need extended surfaces, and what do we mean by extended surfaces? So let's understand this with the help of an example. Okay, let's say we have a plane wall which is at temperature Ts and has an area A1, and the surrounding temperature is T infinity, and the air is blowing over the surface of the wall and has a convective heat transfer of H, and it's losing heat to the surrounding through convection. Okay, so let's say Ts is greater than T infinity. So by Newton's law of cooling, your Q convection will be H times area A1 into the temperature difference Ts minus T infinity, right? So what extended surfaces do, or why do we need extended surfaces? The main reason is that we require extended surfaces to enhance the heat transfer rate. So we want to increase Q. Okay, we want, our aim is to increase the Q, or the heat transfer rate, from the surface that we're interested in. So say if you're looking at a car radiator, you have a limited space, and there's a limited dimensions above which you can't increase the size of your radiator. So what do? You apply different extended surfaces in order to increase the rate of heat transfer, so that the within the same dimensions your radiator can uh, enhance the heat transfer and cool your engine more efficiently. So what are the two ways in which we can increase Q? So we can't change the heat transfer coefficient, but we can change the area. That's the area through which heat transfer is occurring. So we can increase this, and maybe we can increase delta T, but like the base temperature or the temperature of the surface will remain unchanged. So let's see how we can increase the area. So what we do is we introduce extended surfaces like these to the base, which increases the area, the effective area through which heat transfer is occurring from A1 to A2. So now your A2 is greater than A1. Okay, what will be the heat transfer rate in that scenario? Your H is same. You have area A2, and let's say the temperature difference still is Ts minus T infinity. So if your area is greater, if you have increased your area, this should be A1. This means that your Q convection 2 is also greater than Q convection 1. So there, by just introducing small extended surfaces, you have enhanced your heat transfer rate. So this is what we call as extended surfaces, or in many applications we call it as a fin or a set of fins, and these fins can be in different shapes and sizes. So anything that you attach to a surface to enhance your heat transfer rate is called as fin. Now you can have fins of all different kinds of shapes and sizes. You can have fins or extended surfaces which look like cylinder, or which have varying cross-sectional area. You can have fins which look like disc around a cylinder maybe or a pipe. You can have square fins around a heat exchanger, and there is a lot of uh, different kinds of extended surfaces that you can have. But in this video, we will be looking at, or we will be focusing on finding the heat transfer rate through this fins and finding an equation or how to formulate the heat transfer rate through this fin. So let's say we have a solid whose surface is exposed to a fluid at T infinity and has a heat transfer rate of H. Okay, and let's say the surface temperature is Ts, and let's assume that the fin that we have is of a cylindrical shape. Okay, so let's say this is the fin that we have. This surface, which is usually called the base of the fin, has an area AB, and let's say the fluid is flowing this way. So let's say that QF is the heat transfer rate at the base of the solid where conduction is happening. So in this particular scenario, say we have steady state. So in steady state, the heat conducted in at the base is the total fin rate, fin heat transfer rate. Okay, so the QF here, so QF is the total fin heat transfer rate, and we can write QF by QF as minus K times AC, and I'll define AC just in a moment, dx at x is equal to 0. So your x is the direction which is away from the base, so x, and so the base will be x is equal to 0, and AC is the cross-sectional area of the fin. So there will be conduction or conductive heat transfer that will be flowing in the x direction, across the fin. Sorry. Okay, so we define the fin heat transfer rate QF as minus K AC times dt by dx at x is equal to 0. So this is the heat transfer rate at x is equal to 0. So this is what goes into the fin. Now, because it's at steady state, whatever goes into the fin shall be lost by convection at steady state. So we can say that QF will be equal to, say, it's lost by convection through the surface of the cylinder that we see. So there's air flowing across this, and the surface area of the surface is AS. So let's say we have a small tiny particle at x is equal to, say, at a location x, and the thickness of this particle is, say, dx. Okay, so what will be the convective heat transfer across this small particle. Let's take a different color. So let's say the convective heat transfer across that particle will be, let's say, Q double prime convection is the heat flux into the small area. That's the, let's say, the area of this surface area of this small element, which will look something like this. So this element will have an area of, say, DAS. Okay, so this will be the uh, convective heat transfer through that element, and the total convection across the entire fin surface will be the integration of this over the entire surface. So we can write down the formula for QF, which is the heat transfer rate that goes in, as the integration over the entire surface of the fin, times we can write the Q double prime convection, that's the heat flux due to convection, as H times the temperature difference. The surface temperature is, say, Tx, so it's variable, minus T infinity, that's the surrounding temperature, times the area, which is Ts. Okay, so this is like a general formula if you have a cylindrical fin. Now let's define a parameter called as fin performance. Now what is fin performance? It's it's like efficiency, but it's how much more heat, okay, how much more heat is transferred with the additional fin. Okay, so it's denoted by epsilons of F. F stands for fin, and defined as QF, that's the heat transferred with the fin, divided by heat transfer if there was no fin. Okay, so this will be QF, and we can use the formula that we have found out here. If you have a cylindrical fin, divided by if there were no fin, your heat transfer rate would have been H times AB, that's the area of the base, times temperature of the surface, minus T infinity. Okay, so this is something to keep in mind. But there's another parameter which is different from fin performance, and it's the fin efficiency. Now, what is fin efficiency? It compares the fin rate to an ideal max Q heat transfer rate. Let's say it's Q max when your T of X is equal to your surface or the base temperature. Let's say it's, so your Ts is the base temperature, Tb. So what this means is that if, say, the entire fin is at the base temperature, that means the entire fin has like maxed out, it can't get hotter than that, so it's at the base temperature. That will be the ideal case, which obviously won't be possible in a realistic world. So we compare the base fin rate with that ideal case, and in that scenario our efficiency will be QF divided by Q max, which will be our QF divided by H into now the area is the total area. So that's the difference. In for fin performance, you just have the area of the base. Here you have the total area minus the multiplied by the temperature difference. And now the temperature difference is, because the entire system, that's the base and the fin, are at a surface temperature of Ts, our temperature difference will be Ts minus T infinity. Okay, and that's our formula for fin efficiency. So it's different from fin performance. So fin performance is denoted by epsilon of F, and the formula will be QF divided by H into area of the base multiplied by Ts minus T infinity. That's heat transfer rate if there was no fin, whereas for efficiency you compare it with the maximum or the ideal maximum heat transfer rate possible, and the formula will be QF upon H into the total area into Ts minus T infinity. So your total area will include the area of the base plus the area of the fin. Okay, so do not confuse between performance and efficiency. They are two different things. Now what if, now this area is only true if you have one fin. What if you have, say, n number of fins? Your total area in that case will be n times the surface area of each fin plus the area of the base. So here n is the number of fins, As is the surface area of each fin, and AB is the exposed, and the word exposed is important, exposed base area. Okay, so let's now formulate the temperature distribution in an extended surface. Okay, so let's look at a side angle view. Let's say this is your base, and you have a fin which looks something like this, and your uh, base fin rate is Qx. Let's take a control volume. Okay, so this is your control volume, that's your x direction, and let's say the thickness of this control volume is dx. The heat lost from this particular control volume, let's color it in a different color. Let's say the heat lost is dq, and let this be at a distance x from the base. Okay, so this is the problem that we have. Now we'll apply conservation of energy, which is the standard equation that we always use. E steady state is equal to Q in minus Q out plus whatever is generated. Okay, now because we're assuming that it's a steady state problem, this will go to 0, and because there's no heat generated, our last term will go to 0 as well, and this will give us Q in equals to Q out. Now we can write the Q in or Q at X as, let's say we can write, let's use a different color. Let's say our Q at X is equal to Q of X. Q at X is Qn, and our Q out will be Q at X plus Dx. That's the conduction at after the control volume, that's at a location X plus Dx, plus the heat loss due to convection, that's dq convection. So the heat or the conduction through this part, which is Q out, this will be Q out and will be equal to Q of X plus dx. Okay, so let's try to expand this. Okay, so our Qx will be equal to, we can write the Q of X plus dx from first order Taylor series expansion. So let's do that. So our Q of X plus dx will be equal to Q of X plus del of Q of X by del X into dx. So this is the first order Taylor series expansion. And we'll substitute this in here. And we'll get our Q of X, which is the left hand side. And on the right hand side, we'll have Q of X plus del Qx plus by del X times dx plus the convective term, which is dq convection. Now we can write the dq convection as by Newton's law of cooling, but before that our qx's cancel out and we have 0 on the left hand side, and that 0 will be equal to del qx by del x into dx plus the, we can write convection as h into the areas, into the surface area of that small control volume, which is dAs times the temperature difference, and the temperature difference, the temperature of that control volume is T of x, and the temperature of the surrounding is T infinity. Now for Qx we can use Fourier's law to write Qx, and we'll get an ordinary differential equation as KAC, that's the cross-sectional area of that control volume, times dt by dx times dx. So this dx is what we have, plus h into dAs times dx minus t infinity. Okay, so we have the cross-sectional area here and we have the surface area here. Okay, so we need to keep this in mind. Now we can divide this whole equation by k times AC, so this term right here, and let's assume that let's assume that our cross-sectional area is constant and we have constant thermal properties. So we can take KAC outside and we'll divide the equation divide the equation through by k times AC, and uh, we can also write dAs by dx, that's the area divided by the thickness, surface area divided by the thickness of the control volume, as the perimeter at that particular location. So if you divide the surface area by the thickness of that volume, you'll get the perimeter of that control volume at that location. And on doing that, our equation becomes d square t by dx square minus h times the perimeter divided by k into AC times t at x minus t at infinity equals to 0. So this is the second order differential equation that we have if we have a cylindrical fin, and to find the temperature distribution we need to solve this second order differential equation. Okay, so this is the differential equation that we got. Now to solve this to find the temperature distribution using this differential equation, what we'll do is we'll define some new terms. So let's define something called as a temperature axis. Now what is temperature axis? So we define theta of x as temperature axis, which is nothing but the delta t that we have, that's t or t at x minus t at infinity. Okay, and this is nothing but the potential of the system to do heat transfer. So if say your temperature at x was equal to the surrounding temperature, your potential of doing heat transfer would have been 0. So there was no potential of any heat transfer there. But say if you have a temperature difference, that means there is some potential of heat transfer occurring. So, and you'll see why we've defined a new parameter here. This is just to simplify the second order differential equation that we have and find a solution to it. So if we define this, let's see how our uh, temperature or how our dq or d theta by dx look like. So taking the derivative of d theta with respect to dx, this will be dt of x by dx minus uh, dt infinity by dx. Now this is a constant value, so it will be 0. So we get d theta x of dx equals to dtx by dx. So our second order differential equation doesn't change that much. We also define another term or as m square, and you'll see just in a few moments why we've defined m square instead of just m. So our m square will be equal to h p k by k times AC. So we've just taken this term and said that that term is equal to as m square, and this is just so that our equation looks pretty, and it has some significance as well, which we'll see in a moment. So After defining these two terms, our differential equation turns into d theta by dx minus m square theta equals to 0. Okay, so this should be square, dx square. So the m here is called as the fin parameter, and that's because it defines the fin properties. So it has the perimeter of the fin, cross-sectional area of the fin, and the thermal conductivity of the fin. So that's why it's called as the fin parameter, and it's m. So m here is called as the fin parameter, and your m square is defined as h into p divided by k times the cross-sectional area. Now the solution to this differential equation is a standard solution. You need not solve this differential equation, but you can just remember this or refer to the book for the solution of this equation. And the solution for this equation is theta of x equals to c1 times the hyperbolic cos of mx plus c2 times the hyperbolic sine of mx, or you can write this in terms of exponents, and if you do that, your equation will be c3, which will be a different constant of integration, into e to the power mx plus c4 into e to the power minus mx. So you need to remember or know what the solution for the differential equation is, and you can use either of the two forms depending on how your problem is and uh, what given parameters, what are the given parameters. And see, you see m here and not an m square, so that's the reason why we defined this particular parameter as m square. Otherwise we would have got an under root of m there, so that's the reason. Okay, to solve for these constants or to find these constants, we require boundary conditions, and because we have two constants, we need two boundary conditions. Now for an extended surface, you can have four different kind of boundary conditions. So let's see what kind of conditions you can have. So let's say at x is equal to 0, that's your base. Your theta at x is equal to 0 will be a temperature at the base minus T infinity, which can be written as theta at base. And let's say your x is equal to L is the tip. Okay, so the first condition that you can have is convection at tip, and this will give you minus k AC times dt by dx at x is equal to L equals to convection at the tip. So your cross section area of the fin multiplied by the temperature at L, that's the tip, minus T infinity, or you can write this down as minus k AC times d theta by dx, and we saw that dt by dx is equal to d theta by dx at x is equal to L will be equal to your h a c times theta at L. So this is the first boundary condition that you can have. The second type of boundary condition can be that your tip can be adiabatic. So what does that mean? This simply means that there is no heat transfer rate at x is equal to L. So your d theta by dx will be 0. The third type of boundary condition that you can have is that you might be given a temperature of the tip. So you may know the temperature at tip. So your theta at L may be some finite value theta L. So that's the third kind of boundary condition that you can have. And the fourth and a very interesting boundary condition is if the problem says that you have an infinitely long fin. Now what does that mean? So if you have an infinitely long fin, that means if the length of your fin goes to infinity, and this is how you will write this boundary condition, this means that the fin is long enough for so that the temperature at the tip of the fin, let me write this down properly. So the temperature at the tip of the fin will almost be equal or will tend to the surrounding temperature. Because the tip of the fin is so far away from the base, the temperature of the tip will almost be equal to the temperature of the surrounding. And what this will translate to is that your theta at L will tend to 0 because theta of L is T at L minus T infinity. So these are the boundary conditions that you must remember. These are very important, and you should be able to identify which boundary condition to use based on how the problem is framed. And the other thing to note is that these are not sines and cosines. So these are not your trigonometric sines and cosines, but these are hyperbolic uh, cosines and sines. So don't make the mistake of confusing them with regular cosines and sines.